Welcome to this special gathering hosted in partnership between the World Affairs Council of Jacksonville and Jacksonville University's Marine Science Research Institute. It's great to be back on the JU campus. Thank you to President Tim Cost and to Dr. Quint White, Executive Director of the MSRI, for this partnership. Of course, it's you, our World Affairs Council members, sponsors, and partners that make our events possible. Thank you for your support. Thank you as well to our multi-year platinum sponsors listed in the program and to tonight's sponsor, Crowley, represented by its leadership, Parker Harrison, Shandy Bowman, Jen Leonard, and Jim Bender. Our gatherings are made vibrant by your participation, so please text us your questions as they occur to you. You will find a number in the program on the inside right of the program, so please do participate. We will collect your questions, and Dr. Brian Franks, the interim director of the MSRI, will pose them to our guest at the conclusion of her presentation. And now I would like to introduce Dr. Helen Czerski. Dr. Czerski is a physicist and oceanographer at University College London, the author of Blue Machine and Storm in a Teacup. She is a regular science presenter on the BBC and a columnist for Focus and the Wall Street Journal, writing about the physics of everyday life and the oceans. As Carl Sagan helped us to see the cosmos, Helen Czerski helps us see the rules of the universe in the world around us. Our motto at the World Affairs Council is bringing the world closer. It's with pleasure that we present Helen Czerski, whose motto could be bringing the magic of the physical world closer. Please join me in welcoming her.
Thank you for that very kind welcome, and thank you so much for welcoming me here to Jacksonville. It's really lovely to be here and to share this evening with you, and it's really great to see so much enthusiasm for marine science and a campus that's got that kind of focus. I'm going to talk to you about the ocean, but a lot of this is about how we see the ocean, because I think that it's interesting when you look back at how we see the ocean, how we talk about it in society. I think we're missing a few tricks, and I'm hoping that, by the end of the next half hour, I'll have opened some doors for you in how we think about it and how we could think about it. But I want to start with this map here. This is known as the Spillhouse projection, and the guy who came up with it, Athelstan Spillhouse, in 1942, said something very profound. He was thinking about the problem of how we take a spherical globe and we set it out on a two-dimensional piece of paper. And he said that in order to see the land, we always cut the ocean. And so in order to see the ocean, we must cut the land. And this is his attempt to do that. And you can see that what he's done, of course, all these maps are distorted. It's hard to get a sphere onto a flat piece of paper, but he's unwrapped the world by cutting the land, and we can see the global ocean. You'll be able to recognize the continents in the middle. And when you look at the ocean like this, what you can see is it is connected. There is one global ocean. The golden arrows represent some of the major ocean currents. But the thing is that this is one entity. It's a single engine that controls what happens on planet Earth. But it's interesting that we don't talk about it very much. And I wanted to read to you, so Lewis Carroll, he who wrote Alice in Wonderland, was a famous writer of nonsense, which is a specific segment in the English literature canon, underappreciated in my view. But he wrote a nonsense poem called The Hunting of the Snark, and it was published in 1876, which is relevant. And the story is that a group of people get together, they go hunting for the snark. We never really find out what the snark is, but their great adventure starts with crossing the sea in a boat. And the bit of the story that I'm going to read to you comes from the point where the bellman, who's the captain of this boat, has brought his map to show it to all of the people who are going to come on the boat with him. And this is how it goes. He had brought a large map representing the sea without the least vestige of land. And the crew were much pleased when they found it to be a map they could all understand. what's the good of Mercator's north poles and equators, tropics, zones and meridian lines? So the bellman would cry and the crew would reply, these are merely conventional signs. Other maps have such shapes with their islands and capes, but we've got our brave captain to thank. So the crew would protest that he's brought us the best, a perfect and absolute blank. Now, of course, the joke in the poem is that the bellman has come to sea with a blank piece of paper to navigate across the ocean. But actually, it's interesting because this is how in society we tend to see the ocean. If you listen to the public debate, we talk about the ocean as though it was a blank, a void. And the reason that the date is interesting here is that 1876 was the year that the first global oceanographic research expedition came home after 4 years at sea. HMS Challenger had done a survey of the world's ocean, took 4 years, all around the globe, and had came back to land. And so 1876 was when that data came back and the specimens were starting to come back. And so for the first time, the Western world we're starting to see what the global ocean really was, even though it was just the beginning. And so it was perhaps the last year in which we had any excuse to call the ocean a blank, because scientifically at that point, it was quite blank. But 150 years later, we still think of it as a blank, and that is a problem, because we've done 150 years of marine science, people at this institution and many, many others, and we know all kinds of things about the ocean, and yet somehow it's still blank to us. And I think it's particularly interesting when you consider this photo here. So let's go back to the Apollo missions. And the Apollo missions, people went to the moon, but really what Apollo gave us was that we properly looked at Earth. And there are two famous photos that really changed the way we thought about ourselves. One was Earthrise, taken in 1968 on Apollo 8, and that was looking over the surface of the moon back at a partially lit Earth. And then this one, 1972, Apollo 17, on their way out to the moon. And the thing that is striking about this photograph is that they were lined up with the sun completely behind them, so they were looking at a fully lit disk of the planet. And this was the first photo taken where that was the case, because you have to get a long way away from Earth to really see it properly. And so this image came back, and of course it changes humanity's how we thought of ourselves. And it was called the blue marble. So for 50 years, we've talked about ourselves being a blue planet, about living on a blue planet. David Attenborough and others have made these documentaries called Blue Planet. And yet we never think about the blue. When we think we're talking about the blue, quite often in society, we're talking about the things in it, the fish and the whales and the pollution. And of course, they're all important, but they're not the water itself. And the water itself is the big story, because this is the engine. This is the engine that matters, a fluid engine that surrounds the planet and that basically provides the conditions that we take for granted, that influences our lives in more ways than we're ever aware of, because we just take what it does for granted. So I can't... So the problem with all of this, really, the problem with talking about the ocean, the reason that perhaps we're not very good at it, is because it's so many different things. It does very big things and very small things and very fast things and very slow things, and it matters for animals and for humans and for, whatever life is out there. And so it's lots of different things. And I think of this as being a bit like the three, there's an ancient story of the three blind men and the elephant, where three blind men somehow come across an elephant, and one reaches out his hand and touches the trunk and says, oh, an elephant's like a snake. And one reaches out his hand and touches a leg and says, oh, an elephant is like a tree. And the thing is that they're true, but they're partial truths. And the ocean is so rich and complicated that no one way of looking at it is enough. And so I think the way to build up a picture of what the ocean really is, to fill this odd gap in our society's view of the ocean, is to tell lots of stories from lots of different perspectives, so that all those partial truths eventually build up into what the ocean really is. Now, I have only a limited amount of time in this talk, and so I cannot tell you all the stories of the ocean. But what I'm going to do is pick out a few along the way that just give an example, just, open little doors into why it matters and how we can start to think about the mechanisms of the ocean, what this fluid engine is doing and why it matters. So, thing number one is that the ocean is structured. We tend to, again, the popular image of the ocean, and I'm sure that here, given where you are, you know a little bit better than this, but the popular image that it's just kind of a big pond. It's all sort of just a big pool of water that's kind of the same. It might change slowly from place to place, but that is not the case. The ocean has anatomy. It's got structure. And there's just one example of that. I want to tell you a little bit about this thing here. So this is a Greenland shark. It's kind of a baggy sweater pretending to be a shark. It's very, it swims extremely slowly, sort of a few centimeters per second. They can be huge, like 4 to 5 meters long. They live in very cold water. Most of them are actually blind, so this one hasn't got it because, you know, I thought I would not scare people too much. But most of them have got a kind of parasitic worm hanging out of their eye, so that stops them seeing. But the thing about them that's most dramatic is that this is the longest lived large animal that we know of. They can live up to 450 years. They don't reach sexual maturity until they're 150. And the reason that they can live so long is that they live slowly. And the reason they live slowly is that they live in the cold, because cold slows everything down. So in the deep, dark waters of the Arctic, these things are sliding around in the darkness. And if that doesn't give you nightmares, you're more robust than I am. Anyway, so we have an Arctic shark. So let's take a look at a map here of the North Atlantic. The colours of the ocean represent the surface temperature, and you can see we've got nice, warm, deep reds in the tropics, and then closer towards the poles, the dark blues represent much colder water around freezing. And so this is where you'd expect to find a Greenland shark, up in the cold water up there, and that generally is the sort of place where they live. But in, I think it was 2013, there was a survey ship down here in the Gulf of Mexico, and what it was doing was looking to, trying to measure the consequences of the Deepwater Horizon oil spill. So they were doing biological surveys, putting down baited hooks, seeing what came back up, comparing before and afterwards. And the Gulf of Mexico is very deep, so they put down a hook, 3 kilometers, comes back on deck, and the thing that was pulled out was a juvenile Greenland shark. And they weren't that surprised. They were a bit surprised, it was a bit unusual, clearly a bit out of place, but they weren't that surprised, because this is the general picture over most of the global ocean. Simply, so when we're talking about the structure of the ocean, we have to start thinking about its different parts. And this is kind of the simplest one, that there is a warm layer floating on top of the deep ocean. That warm layer, generally a few tens of meters thick, depends on what's going on, and you have cold water underneath. So even though that surface temperature map that I showed you showed the Gulf of Mexico as being deep red, 30-degree water at the surface on the day that shark was pulled on deck, down at the depths, it's only 4 degrees. So the shark was a bit lost, but it wasn't way out of its temperature range. And when they pulled it onto the deck, it was warmer in death than it had ever been in life, which is quite a strange thought. So the point is that this structure, this is only the simplest start of the structure of the ocean, that we need to think about it as having components that move over each other, that are doing things, that are dynamic. And this is where the engine comes in, that these different areas of water are moving around and the whole thing creates a single global engine. So I am going to move on from that engine itself to some of the passengers that it carries. And the second half of the book is written in terms of messengers, passengers, and voyagers, because these are the things that travel through the ocean one way or another. And the passengers are the ones that get carried passively. So here is a thing, an unusual passenger, to get us started on passengers. So here we are. This is the coast of the continent of Africa. We can see the Indian Ocean on the right-hand side. And we're going to zoom in on this bit of coast here. And there's a little town in there that's called Kimbiji. And Kimbiji, so being right on the edge of the Indian Ocean, this is the kind of place where you get sea turtles, where sea turtles kind of haul themselves up onto a steep beach, dig a hole, lay their eggs, the females, and then go back out to sea. And because sea turtles are clearly not doing so well, there are quite often monitors, sea turtle watchers on the coast in Kimbiji, looking for sea turtles that come up onto shore and making sure no one disturbs them. So, a few years ago, there were 2 sea turtle watchers there, and they saw something that was about the size of an upturned kettle drum coming out of the ocean, only it wasn't pulling itself like this, it was walking. And it was walking because it was a tortoise. And here it is. This is the Kimbiji tortoise. Now, before any of you start to question the biology you were taught at school, it wasn't meant to be in the ocean, right? This is not a place tortoises are supposed to be. This one had been there quite a long time. It's covered in barnacles. It had been floating around for about 2 months. It had floated, it turns out, 800 kilometers from the island of Aldabra. Now, tortoises are not meant to be in the ocean. Generally, if a tortoise ends up in the ocean, the odds are not very good. But if it does, take a few too many steps into the surf zone, it's got a few advantages. One of them is that it's got a nice long neck, so it can stick it up, use it like a snorkel. One of them is that it can go a long time without fresh water or food, so that's very useful, ups your survival chances. The real kicker is that the females can store sperm. So if they get themselves sorted out before their clumsy morning of falling in the ocean, and they happen to wash up somewhere else on the other side, they can start a new colony all by themselves. And this is very relevant. Oh, that's a tortoise that fell in. So let's look at the other bit of the world. So there's two places in the world where that are famous for their giant tortoises. And the Galapagos Islands, apart from Darwin and his finches, the thing they're famous for is giant tortoises. Now, I don't know if you've ever asked yourself how the Galapagos got its tortoises, but it's an interesting question because the Galapagos are volcanic islands. It has never been possible at any point, and they're relatively young, so it's never been possible to walk from the mainland of South America to the Galapagos. And I'm sure you can see where this is going. There is, oh, that's a Galapagos tortoise. So there is this current that runs up the side of South America along the coast, and then it turns outwards to go out into the Pacific. And it turns out that the reason the Galapagos has got tortoises is because over long, long periods of time, against all the odds, a small number of tortoises have sort of wandered into the ocean by accident along that coast. And then they all get carried in the same direction, get carried out across those islands. And there's a higher, most of them will have died, but there's a chance that they'll end up on one of those islands. And once you have a population of tortoises, you get island gigantism, and then you've got a population of giant tortoises. And it's the same in the Seychelles on the other side. So the Kimbiji tortoise came from Aldabra to the main continent, but those are reversing currents, so it can go the other way. And the point about all of this is that if the ocean can carry something the size of a tortoise, it can definitely carry quite a lot of other things. And a lot of those other things are very, very small. Most of them are too small to see, but they are really, really important. And they matter for us. It's not just about the ocean and them being the fabric of life that is woven through the ocean engine. They do matter for other things as well. So just as an example, here is the Colosseum and the Pantheon. So two very famous ancient buildings that are in Rome. 2,000 years old, both of them, more or less. And they are both made of concrete. So a lot of the foundations of the Colosseum are concrete. The Pantheon, that's the largest unreinforced concrete dome in the world, even now, 2,000 years later. The Romans were really good at concrete. And today we tend to think of concrete in a slightly different context, right? We know it's the foundation. We know it's necessary for skyscrapers. There's all these sort of modernist buildings. If you're a fan of a brutalist architecture, I am not. Concrete is your favorite thing. And it is interesting. I mean, whatever you think of the merits of concrete, it is an artificial rock. You can shape it to whatever shape you want. It's immensely, it's very flexible in the sense that you can do lots of things with it. You can create your own stone. So architects have always been very interested. Concrete's a useful material. And of course, our modern world is built on concrete. It's the second most, after water, and I'm not sure why water counts as a thing we produce, it's the second most produced thing in the world. So I think the number is 1.4 cubic meters for every human on Earth every year. Astonishing amount of concrete that we generate, that we've built the modern world with. Now, so let's take a step to some sea creatures. Because concrete doesn't just come about by itself. But let's skip to the ocean for a little bit. So this here will be familiar to anyone who's done any marine biology. It's a coccolithophore, which means it's a tiny single cell. It's a sun harvester, so it lives in the top layer of the ocean, and it will harvest the sun's energy, and it builds itself basically out of the material it can see around it, fueled by the sun. And the thing about these things is that if the ocean engine turns in the right way to produce the conditions to bring nutrients to the surface where they can meet the sunlight and you can produce life, you can get gigantic sort of accumulations of these all growing at the same time. So big you can see them from space. And what you're looking at here is a map of the south coast of Britain. So that's Devon and Cornwall. And that is a coccolithophore bloom. So these tiny creatures, even though they're single cells, there are so many of them, you can see them from space. And the thing about this is if you produce so many things all at once, other things can't eat them quickly enough. So when they die, there's bits left over, they fall down to the bottom of the sea. If they build up layer after layer after layer over a long period of time and get compressed into rock, and then if geology pulls them back up to the surface, what you get is the White Cliffs of Dover. And so the White Cliffs of Dover are largely made out of tiny marine sea creatures. And there's a thing I really like about this, which is, so one of the advantages of being in the UK sometimes is that we've got some very old institutions like the Royal Society and the Royal Institution. And the thing about them is that they did some things that you're not allowed to do anymore before they were not allowed. And one of the things that they did, the Royal Institution has a piece, so you're not allowed anymore to take pieces of the White Cliffs of Dover, they're protected. But they took some samples before it was forbidden. And so a few years ago, I got them to I borrowed from them one of their samples, one of their pieces of the White Cliffs of Dover, and I did something that cheered me up no end. I drew a coccolithophore with itself, which I think is just brilliant. And what is great about this is that, just imagine, all the people taught with chalk, right? History, languages, mathematics, all of this passed on through the medium of tiny, tiny sea creatures, which is quite cool all by itself. Anyway, let's go back to the concrete for a second. Here's our modern concrete building. What do we need to make concrete? We need cement. So concrete is aggregate, pebbles, sand, that kind of stuff, stuck together with cement. So cement is the critical bit. The critical thing in cement is lime. And the critical thing in lime is calcium. And calcium is a really good building material. It's chemically absolutely brilliant at building things. So to get lime, you go back to calcium carbonate. That's what this is. Where do we get calcium carbonate from? Limestone. This comes from the White Cliffs of Dover. And the thing about calcium is that it's extremely good for building things. So the coccolithophore that I showed you, that's built out of calcium. And the reason that matters is that calcium, even though it's a really good building material, in the rocks that come out of volcanoes and things like granites, calcium is relatively dilute. There are no natural samples there are no sort of natural rocks that have huge amounts of calcium. So there's not much calcium in the rocks, the sort of raw rocks from the earth. And then acid rain falls on to the rocks that there are and kind of weathers them, things dissolve, washes them out to sea. And then the calcium is even more dilute. So that's no good. But then those tiny little coccolithophores are building themselves atom by atom out of the calcium ions in the water around them. And the reason that we have deposits of calcium that we can use to make concrete is because tiny sea creatures have collected that calcium cell by cell by cell. And so every single piece of concrete you have ever seen, the foundations of the building that we are sitting in, this came through a marine sea creature. It was the ocean and the ocean's passengers that collected it in order to put it in a form that we could use. So even in places where you think, how can the ocean possibly have anything to do with concrete? It's creating resources and situations and environments that we completely take for granted, but we wouldn't have without it. And I write a column for the Wall Street Journal, as you heard. And illustrators, I'm sure they do their best, but I have had two separate occasions when an illustration for a scientific article an illustrator has drawn an 8-sided snowflake. And I thought, what's the one thing everyone knows about snowflakes? Anyway, but they were all redeemed when this guy here drew this to illustrate a column I wrote about the concrete and the coccolithophores, because it's just such a beautiful expression of sea creatures helping build concrete. Anyway, so the passengers in the ocean have a role to play. So very quickly, I'm going to have a bit of a rant. So let's get to the messengers in the ocean. The messengers are sound and light. Now, I've got a bee in my bonnet about this, made by this guy here, the famous guy with the bobble hat, Jacques Cousteau. And this film, The Silent World, won the Palme d'Or at the Cannes Film Festival in 1956. It was a massive hit. Everyone had seen it. It made a huge impression. because Cousteau was not only one of the developers of what we now know as scuba diving, but he also helped build and helped develop underwater cameras where he could film what he saw in the ocean. And that's what went in. And so he showed the ocean, the underwater world as it really is, to the public for the first time. Now, I'm always hesitant about criticizing the great pioneers of people who talked about the ocean. However, I've got two problems with this film. One of them is that it has not aged well. And I didn't realize this till I saw it 2 years ago, but it's absolutely horrific. They ride sea turtles, they blow up coral reefs, they run over a baby whale and then watch it die. And the most enthusiastic person on the ship is the chef, because every time they find something interesting, over the side, straight into the pan. He would be put in prison for making this today. There is absolutely no doubt about that. But if you want to believe that attitudes can change, I guess you kind of have to take the positive and say there is no, we can change our ideas about what's acceptable. So that's thing one about it. Thing number two is the name. He called it the silent world. But he, of all people, must have known that the ocean is not silent, because he was a free diver before he was a scuba diver. And he must have known that the ocean is full of sound. And not only that, but sound is the more important messenger in the ocean. Up here on land, we take for granted that light is a long-distance messenger. We can see the moon, we can see distant mountains, we can see things that are a long way away. But we can't hear what's going on very far away. Sound is short distance for us. Light is long distance. But in the ocean, it's the other way around. Light doesn't travel very far. Sound, especially in the right conditions, can travel an extraordinarily long way. And so sound is the messenger that matters in the ocean. And just to give you one example of this and how you can see how much it matters, I went to the Natural History Museum in London last year to see this. This is a curator's hands here. I was down in the basement. The best bits of museums are always down in the basement where all the cupboards are. And what you're looking at is whale earwax. Now, this raises a few questions. Number one is, why does a whale have earwax? And the reason for that is that whales and dolphins evolved from land mammals that were about the size of a mid-sized dog that 50 or 60 million years ago started to live a more aquatic life and evolved into what we now know as whales and dolphins. Now, so the point about that is a land mammal, these land mammals that they evolved from, they kind of had anatomy mostly like us, right? They had lungs and kidneys and they had ears and all that kind of stuff. And it's the ears, obviously, that matter here. So if you become more aquatic and you want to slide through the water with minimum energy, the sticky out ears are a bit of a problem. You've got three, this is just your outer ear, then there's a middle ear and an inner ear, and it's the inner ear where sound is sensed. And the sound is sensed in liquid, and the middle ear is kind of what gets the sound from the air into the liquid, and this is just collecting on the outside. But if you're swimming, this is, your outer ear is literally a drag, getting in the way. So their outer ears shrank as they became more aquatic. But that didn't matter, because they weren't hearing through that hole anyway. If you go swimming today, if you put your head under the water, things will sound different. And it's not just because the sound underwater is different, because you're hearing it differently. Sound comes at you underwater. It's not going to go through your ear, because that's got air in it. But it comes into your jaw and the bones of your skull, travels up your jaw into your inner ear, and that's how you hear underwater, and that's how whales, the baleen whales, hear. And so the whales weren't hearing through the hole. So the whole kind of, skin kind of closed over the top. And actually, if you look, so the Natural History Museum in London has a life-size model of a blue whale. Here it is, in the mammals hall, obviously. If you look just behind its eye, there's those kind of flaps where it opens its mouth. If you look in there, so there's the eye, and then you zoom in there, even on the model, there's a little dimple. And that little dimple is where the ear used to come. That's where the hole, just underneath that is the hole. But now it's sealed over with skin. And evolution's not very tidy. So the whale still makes earwax. It's just got nowhere to go. So it squeezes up the hole like toothpaste until it reaches the skin on the outside, and then just builds up throughout the whale's life. So those lines you could see on the earwax are like tree rings. They're layers. And because they're not part of the whale's body, they're not recycled. Most of us, we're recycled. All of us is a different age, different parts of us, because it's being recycled at different rates. But it's just sitting there, right? So this wax is building up a record of the whale's life. So you get these earwax plugs, and that's one whale's lifetime from beginning to end. But then, see, the scientists from the Natural History Museum and the American Museum of Natural History realized that because curators are very organized, they had lots of these samples and they knew the dates the plugs had been collected, so they knew when the whales had died. So what they could do between the two museums was line up plugs of whale earwax going back 150 years, a global record of whale going back 150 years. And what they chose to do with it was look for cortisol, which is a stress hormone. And sorry for the graph, but you'll cope. Here it is. Here's the data. Here's the plot. So along the bottom, we've got 150 years, going back to 1870. And then the black line, so the axis on the left, that's the amount of whale stress that whales felt globally. And you can see that it goes up and down. So there's a huge amount of variation. There are very distinctive patterns. So what makes a whale stressed? Someone trying to kill it. And on the right, that blue axis is the number of whales that were being killed through industrial whaling. And you can see that someone trying to kill you does indeed make you very stressed. The correlation is very tight. And you can see the end of industrial whaling, the whaling moratoriums of the 60s and 70s, kind of the stress drops off. But there's a place where the pattern doesn't hold. And it's in that shaded area in the middle, and that's World War II. Because during World War II, the humans were very busy killing each other, so they weren't killing very many whales. You'd think the whales would be having a great time. But you can see that whale stress goes right up. And the reason for this is the sound. Guns, bombs, torpedoes, battleships, filling the oceans with sound. And because sound is the way that whales sense their world, it's really stressful. And it's written in their earwax globally. It's quite an astonishing thing. So sound is a really important messenger in the ocean. The way it travels through the ocean's physical structure is really important. So that's messengers. Right, this is the ranty bit. You may have heard, you may even have said, we're not judging, this. We know more about the moon than we know about the deep ocean. And if Helen ruled the world, this would never be heard ever again, because it's wrong and damaging and misleading. And this rant goes on for some length of time, but I will give you the very short version. So the first thing is, it comes from a grain of truth, right? Back in the 60s, somebody noticed that we had mapped the surface of the moon with a greater resolution than we had mapped all of the deep ocean. So that's the grain of truth it's based on. And what problem with that is it assumes that the only outcome of discovery is a map. And of course, this is the Western way, right? You know, for centuries, kings have sent out explorers, often their ships. They got there, they got their sextant out, they mapped the land, they stuck a flag in it, and then they named all the bits of it after all their friends and sailed back home, and the king said, thank you very much, right? This is the way exploration works. And this is not, we have to move on from this idea of exploration being about drawing a map. Exploration has to become about processes. And so if we think about the ocean, you know, first of all, it's got a third dimension, and all of that water is doing stuff, it's busy. The ocean is full of life. It's got little things like this, you know, swimming around, bioluminescing. It's got all kinds of interesting geology. And then, bear in mind, I mean, the moon's got geology, but it literally has not changed for 2 billion years, right? It's just sitting there. The ocean geology is changing all the time. Processes are happening. And then we've got this thing here. Now, there are 3 species that do this thing I'm about to describe to you, and I promise I'm not making this up. Let's start with a sponge, right? A sponge is it's kind of a solid pretending to be an animal, but it's got enough animal in its account, right? So it's an animal, it lives on the seabed, it's kind of porous like a sponge. That's where sponges came from. And there is a particular type of polychaete worm that, when it begins, it's kind of floating about like a larva. And then when it settles with its head down the bottom of the sponge. And as it grows, the tail kind of grows upwards. But it doesn't just grow up through all the holes in the sponge. It branches, and it branches, and it branches. And after a while, when you look at the outside of the sponge, and I promise I'm not making this up, what you see is 1,000 little worm anuses crawling around on the surface, poking about. And then this worm has a problem, right? Because when it comes time for mating, it's not, the dating game is closed to this worm. It's grown through this stationary sponge. It's not going anywhere. So what happens is that the little anuses grow eyes. And the digestive bits turn into gonads. And then the little anuses break away and swim off up to the surface at the same time as all the other worms in the surround. Get on with the mating up there, and then you've got new little larvae, which just, float back down and find themselves a new sponge. Now, you do not get that on the moon, right? There is more science in that one worm than there is in the whole. Now, the moon is very nice, right? I have nothing against the moon. But the problem with this phrase is that every time you say it, it implies that the moon and the deep ocean are comparable, that the state of the deep ocean is just that of a bare rock that does not change. And it is not true. There is a huge amount more to know about the ocean. And sure, there's lots of things we don't know and we need to go and find them out. But it's so much more rich and fascinating and interesting that we cannot allow ourselves to stick with this boring, awful phrase. So if you leave this room with one thing today, make it that you never say that ever again. And if a friend happens to say it, very nicely explain why it's a terrible thing to do. Right, so the ocean is many things, but how do we think about it? What do we do? What's the view we need to take of what the ocean is and what it means? So I have written before about, I think each of us has 3 life support systems. We've got our own body, we've got planet Earth, and we've got the infrastructure of our civilization. And each one of those is a life support system that we rely on. It's keeping us alive. And the ocean is the beating heart of the planetary life support system. The ocean is what sets the conditions for the rest of the planet. It's influenced our history and our culture, the way the world is. All of that depends on what the ocean is and how this engine turns, how this fluid engine turns. That's the critical bit. And so in a few years, maybe next year, the NASA Artemis missions are going to go back to the moon. And for the first time in 50 years, human eyes will be far enough away to see our planet again for the first time. To see it again. And the thing about this is they're going to see this sight and they're going to see a blue planet. And this time, the reaction to it has to be different because this is not about a color. It's about an identity. The light that travels from Earth out into space is our signature on the universe. And we are all a part of this planet. Earth's identity is our identity. And this time, when we're far enough away, we have to look at this sight and we have to see what we're saying to the rest of the universe because it matters and it's a very simple message. And what our signature says is we are ocean. Thank you.
Thank you very much, Dr. Czerski. Fascinating, interesting presentation. I think some of the unique examples that you gave, most of us will find interesting. And now we're going to spend some time, a few minutes, asking Dr. Czerski some questions that have come from the audience. And I think with all the talk about the ocean engine, many people are thinking about how we might be affecting that engine. So a lot of the questions that came in relate to, what we are doing to this ocean engine. So the first question that I'll ask is, it's suggested that a warming ocean is leading to these stronger and more frequent storms, more impactful weather events. Do you believe, based on what we're doing with this ocean engine, that those will continue and even, become exacerbated in the future?
Yeah, and one thing I should say actually is that one of the reasons for writing the book like it is, so most of the book is about how the ocean works, because I think we don't spend enough time talking about how it works before we start talking about how it's changing. And of course we need to talk about how it's changing, but if we don't understand what it is and what it does, that talk of change, it doesn't mean anything and it leaves you feeling helpless. It's like a doctor coming along and saying, well, you've got this disease and it's a terribly long list of Latin words and you don't have any idea what it means, right? I don't know. Does it mean I should never eat broccoli or that I'm going to die tomorrow? So I think talking about what the ocean engine is doing it's important that some of that comes along in society along with talking about the changes. So there's no doubt that the ocean is warming. So what climate change is fundamentally is an accumulation of energy. that carbon dioxide in the atmosphere slows down the rate energy leaves. So it's like a bath, you know, the tap coming in, that the energy from the sun is the same. There's some level of water in the bath. And if the plug hole, if the rate water's going out the plug hole is the same as the rate it's coming in the top, the level in the bath stays the same. If you bung up the plug hole, the level in the bath starts to rise. And that's what's happening on Earth, that the amount of energy in the Earth system is slowly increasing. And so we know 93% of that additional energy is going into the ocean. And it's not just, it turns out the ocean's really good at storing heat. It's actually doing us an enormous favor, but it's still making a difference. And the reason it matters is that the ocean engine doesn't all heat up in the same way at the same time. If you add extra heat energy, it will actually change the shape of the engine a bit. It'll change how it's distributed and how fast it moves. And so because the shape of that engine affects all of the rest of us and the extreme weather and all of that, then you've got a problem. So if we decarbonize rapidly, which we are capable of doing and which we can do, and which we really, really, really need to do, we can slow a lot of the damage. There's a time lag, so some things are gonna carry on happening after we stop burning fossil fuels. But every single carbon atom we keep in the ground rather than in the atmosphere is going to lead to a better future. So there is no doubt that changing the shape of the ocean engine and the speed at which bits of it turn and the speed at which it turns over is going to have a large impact on our society. And we're going to feel it, you know, and it's not a pleasant thing to think about, but we can, how massive the ocean is, and yet we've still affected it, right? We can see these changes happening. So I think the important message is that if we think about what we can do something about this is not a message of doom and gloom. If we think about how the engine's turning and what happens to an engine that you make warmer, we have an incentive to slow down that warming process, to stop doing the things which are damaging. Because the engine is it's an intricate, complicated thing. We are not in control of this. It's not like the kind of steam engine where you can just replace one cog with another cog. That is not the way this game works. It's phenomenally intricate. And so there are these big patterns and then these little patterns and smaller ones. And so I think if you want to do something for the ocean, decarbonization is the thing to do. And that we're going to have to adapt, you know, to more extreme weather. We can see it happening. But every single thing we do to not make it worse is going to really, really matter.
Thank you. And related to that, also there was a few questions that came in about the whale earwax. And in particular, there were a few questions related to, you know, what are we seeing today with those cortisol levels? We also hear, particularly on the east coast of the U.S. this summer, with whales being, you know, coming ashore and dying. You know, there is a potential, or at least a suggested potential link between that and these wind farms. You know, can you speak to that a little bit in terms of how these cortisol levels, even now, and noise pollution are affecting these?
So the graph I showed actually stops a little bit. It's kind of spiky at the end, and I think that's partly because it's harder to get samples now, because you just used to go out, you know, the original samples were captured because you just went out on an industrial whaling ship and there were loads of them, and there's actually fewer samples now because there's not as many whales dying. But there is no doubt that whale stress is on the increase again, and there's multiple reasons for it. Mostly it's changes in temperature. So as the ocean warms, you shift ecosystems, you shift how whales navigate, you shift what's comfortable in different environments. And the problem is that then it all doesn't line up. You know, you've got these systems that this thing comes up here and it expects to meet this thing coming the other way. And if if they delay a bit because it's too warm, maybe they miss each other, that kind of thing. And pollution, overfishing, noise is definitely a part of it, but I think the far larger impact on whales is commercial shipping. There's a lot of effort going into, there's a lot of questions being asked, I think, not a lot of answers being given about how to make commercial shipping quieter. It is the bigger problem. So wind turbines, you know, we need a decarbonized world. Wind turbines are a good source of renewable energy. Actually, it's interesting, in the US, renewable energy for you is 80% solar and 20% wind. And in the UK, it's almost exactly the opposite way around. We have 80% offshore wind energy in the North Sea. And so the problem with the sound isn't actually the operating. I mean, there's a little bit of sound, but compared with all the ships, it's nothing. It's the pile driving to put them in. But we're finding ways to shield piles. So as a bubble physicist, there's actually a lot of that involves newer technologies that will use bubble-like things. The current ones don't work. There are ways to shield as you're driving the piles. That's actually the noisy bit. And then, and wind, wind turbines. So, and there will be floating wind turbines. We're not very many years away from having floating wind structures that will be anchored, but are not, that you don't need to drive the piles. So you've got rid of your major source of noise. So I don't know the details of the whales off the coast here, but I think that the sound of a wind turbine in operation is the least of those whales' problems. That would be my perception.
And then I think one more, and more kind of on a personal path level. A lot of marine scientists, at least marine biologists, they learn and get interested in the animals and then kind of go down from there. Your career starting as a physicist, I won't lie, experimental explosives physics sounds like a pretty cool PhD. Can you speak to how...
You spend a lot of time clearing up.
Can you speak a little bit to how starting kind of as a physicist and then moving into the marine science and the ocean world maybe shaped things in your mind a little bit differently?
So I'm a mechanisms person. I care about how things work, and I'm always looking for the sort of more fundamental thing in the how it works thing. So that's why I did physics, because I wanted to pick apart how things really worked on a physical level. And my PhD I ended up doing it because, I was in the Cavendish Laboratory in Cambridge, which is a famous old physics lab. It's got a lot of people that do cosmology, a lot of people that do quantum mechanics, and then there's kind of this bit in the middle where people do what is called condensed matter physics, or was then, which is kind of the physics of solids, basically on a small scale, but not super tiny, kind of things you can pick up. And I was interested in that world because I wanted to do science of something I could see and, could touch. It was tangible. And so the explosives, really I started off with impact experiments, and then it just so happened that the PhD that became available was what happens can you see what happens just before an explosive goes pop? So you hit it very hard with something, things change in that material before it goes bang, in microseconds. Can you see them happening? And I was interested by that game. Can you see what's happening just before it goes pop to the molecules themselves? And so I built experiments to do that, and I was not interested in blowing things up. And I had to do a lot of clearing up anyway. But the point was it gave me skills in high-speed photography and in looking at very small things happening very quickly. And when I looked for something that wasn't explosives, that took me to the world of bubbles, which are small and do things very quickly, and that took me to the ocean. So it's not a linear path, but I think it's quite interesting that being interested in mechanisms can take you in a lot of different directions. And I think some of my colleagues who I did my PhD with are probably still studying that. But not very many, actually. It's taken us off in a lot of different directions. And I'm the kind of boring, having seen a lot of explosions, I'm kind of the boring person in the room when it comes to action movies, because what I see are, I've seen lumps of metal kind of ripped apart, and the thought of that happening to a human is completely abhorrent to me. And, build all these things that humans carefully construct, and to rip them apart like that, I find that really hard to watch, because I've seen on the microscopic level what it does to things, and it's really horrible. So I was very happy to move away from explosives, but it got me into bubbles, so I can't complain.
Okay, well, thank you very much again, Dr. Czerski. And then, the last section, I'd like President Tim Cost, Dr. Quentin White, and Mr. George Robbins to come up on stage for the awarding of the 2023 Marine Science Pioneer Award.
Dr. Czerski, you're anything but boring. Thank you again for coming. Well, Dr. Brian Franks, who's the interim director of the Marine Science Research Institute. I'm Quentin White, and I'm the outgoing executive director of the Marine Science Research Institute. And joining me on the stage is President Tim Cost, a JU graduate who we're proud to have back in our leadership role, and we appreciate him being here tonight. George Robbins, who you have heard about earlier, he's the, He's the chair of the Marine Science Advisory Committee, and they're the ones who helped sponsor this in terms of helping raise the money to do this. We also appreciate the sponsors, and you heard Dr. Jackson iterate those. One of the reasons we do this every year is to bring world-class scientists to JU to listen and speak to our students. And this afternoon at the MSRI, Dr. Czerski was nice enough to sit and answer questions from our students. And so we really appreciate that. And so as part of that, we want to give this award, which is the 2023 Marine Science Pioneer Award for someone who really is paving the way. And we really, really appreciate you being here, Dr. Czerski.
Just very quickly, like to say thank you so much. I really appreciate your enthusiasm and your support, and this is a really lovely thing to have. But really what this is a symbol that we can all think about the ocean more, and that this is a good direction to be going in, and let's take the blue with us. Thank you all very much.
Thank you again for coming. Thank you to the World Strategies Council for sponsoring with us. Safe travels as you go home. Good night.